So at this point, we've talked about decomposition, but in this super high level example of a morning routine, what does it look like when we apply it to code? Well, the best way to think about that is to actually choose a problem and dive into it. So I wanted to have us actually try and solve a problem, and it's called Mountain Carol. And the idea behind Mountain Carol is we want Carol to scale a mountain. The mountains are always going to look a bit like this. They're always going to go up with a slope of 1 and down with a slope of 1. Carol's always going to start right in front of the mountain and is always going to end right after the mountain. And Carol should place a beeper at the top. So like most people in California, it seems that Carol also likes to go hiking. Now, I want you to think about how you would solve this problem. Like, what if I asked you, go code this? How would you approach it? How would you break it down? What would your solution be? So I'm actually going to encourage you to pause your video in 5, 4, oh, you should pause your video for about like a minute. Go think about this. Go for a walk. Actually, don't go for a walk. Shelter in place. That's important. Think about this. Come back in about a minute. In 5, 4, 3, 2, 1. So presumably that was like a minute for you, but it was just a couple seconds for me. Anyways, so hopefully you've had time to think about how you would solve this problem. And just while we're warming ourselves back up to the problem, remember, we want Carol to solve this problem. That idea you have, your strategy, how you're going to solve the problem, there's a special word in programming for that. It's called an algorithm. When you have a cool idea, like a solution to a problem, and you can describe it in words, it's like your strategy in coding. That's what we call algorithms. And the name of algorithm, just fun fact, comes from this Iranian scholar whose name was Muhammad al-Khwarizmi. He invented all sorts of cool things, including the concept of algorithms and some of the world's earliest algorithms. Anyways, it's not important why it's right now. What is important is how we're going to get to the top of this mountain, guys. You guessed it, we're going to use some decomposition. Now, before we jump in, though, I want you to know, as we get more complicated in Carol, we're going to start assuming that the programs you write, your algorithms, they shouldn't just work for one world. If you just had to have Carol climb that one mountain, it's not too hard. But you should be writing a program that can climb any mountain if it's the right shape, no matter how small. So it could be this like dinky little molehill. It could be this like pretty respectable mountain, or you'd be like the Mount Everest of mountains. Like we want Carol to be able to solve all of these problems. So like, how are we going to solve this problem? If we want to solve this problem, an interesting thing for you to know is that when experts want to solve problems, they don't start with code. Often they'll think. When I'm working on a problem, nowadays, mostly research problems, I spend about 80% of my time thinking, and maybe about 10% of my time coding, and about 10% of my time telling people about what I did. Thinking is a big part of coding. So before we jump into the code, I want us to think about it. I want us to think, how are we going to solve this problem? So, what do we want Carol to do? On a high level, what we want Carol to do is we want Carol to be able to scale a mountain and put a beeper on top. So this is our goal. But what we learned from that morning example is that, like, hey, if you have a big goal like this, maybe you shouldn't just start with like low-level commands like moves and turn lefts. If you have a big problem, the first thing you should think about doing is how can we decompose this into bits? And I have a proposal. I think there's a pretty nice way to decompose this. Maybe you have your own way. There's lots of good answers in coding. But we could think about what are all the steps that go into this, like not low level, but high level steps. You could say maybe the process of climbing a mountain is threefold. Step 1, you go up. Step 2, you place your flag. You're like, that's a step? That sounds pretty. It's a step, believe me. Step 2, you place your flag. And then step 3, you go down the mountain. You're like, I don't think you've done that much here, Chris. You basically said that climbing a mountain is going up and then going down. Like, how is that brilliant? And actually, you're right. It wasn't that much work, but that's how we solve hard problems. We take small incremental steps towards the goal. We think, okay, I got this big problem. Let's break it down slightly. But I tell you what, doing this, having Carol just go up a mountain, it's easier than doing the whole problem. So as long as you've broken down your big problem into something that's easier, you've made progress. Now we can choose any one of these and we can break it down even farther. So what's the process of climbing a mountain? Well, clearly there's a while loop. So I'm going to write the while loop. And before I think about the condition, I know there's going to be some sort of condition, like there's going to be some sort of repetition. We can say like while not at the top. Like, what are you going to be doing here? And you might be thinking like, oh, Chris, now it's time for some Carol commands. Like I turn left. I'm like, no, let's see if we can not jump right into Carol commands. I would say the thing that you do is while you're not at the top, you take a step up. And step up isn't something in the Carol vocabulary. So let's say while some condition is true, you step up. Think about what that condition is. I'll get to it in a second. But that's how we're going to do this first piece of our decomposition. And step up, that's something that we can break down even further. Well, let's say step up, what goes into stepping up? So stepping up, I'm going to just draw something to the side, If Carol's here, facing the wall, after you step up, Carol should be on the next step, right? So, okay, we can think about step up now in terms of in terms of commands. So maybe let's turn left, move, turn right, move. You can say like, this is the decomposition of the idea, step up. Now we're not totally done. Turn right's not in the vocabulary, but we already know the decomposition for that. Let's just turn left 3 times. Do you see what I did here? Take a big problem. It's made up of these 3 smaller pieces. Take one of these problems and it's made up of this smaller piece. Take that smaller piece, break it down, and eventually get to the point where you're at Carol commands. And that's that process of decomposition. Take big problems, break them into small ones. That's how you do really cool programs. And if you do this, it's kind of unbounded how cool a program you could make. If you're just always trying to take your problem, make it slightly smaller, you can do some really phenomenal stuff. Okay, anyways, this all looks really good. There's one big honking question left, which is, what's this condition for stopping? So Carol is going to keep taking steps up the mountain. Every time after the step, the post condition is that Carol is facing the mountain again. The answer to what's your condition is the same as the answer to this question. What is always true when you're not at the mountain and is not true when you're at the top? So like, what's different about this context than about when Carol's in front of each of these ledges? So Carol's always in front of these ledges and eventually you get to the top. What's changed? Well, in each of these ledges, the thing that's always the same is that the front is blocked. And when you get to the top, your front is no longer blocked. So I want to keep doing this while my front is blocked. So let's see, front is blocked. Hey, do you guys know, did you notice I'm not writing my underscores? Like this should technically be like front is blocked and there should be some parentheses there. And same with this, there should be underscores here, not parentheses. This is a special thing called pseudocode. It's like almost code, but not really code. It's pseudocode. It's a little bit closer to English and just a little bit easier when you're writing. Like when you're writing, who cares about the parentheses? But like when you're coding, those are really important. Anyways, I've written this in pseudocode. It's almost Python. This is decomposition. And before I solve a problem, like before you do midpoint, do not just jump into the code. Take a piece of paper, try and decompose it, try and think about all the pieces that go into midpoint. Anyways, oh, and that applies for all your problems, not just midpoint. It's also for triple. It's also for, stonemason, Carol. Now we thought about it though. Let's get into the code. So I switched over to Ed so we can code up this solution. Our job is to write the program that's going to make Carol go up this mountain and go down. We've already thought about it, but now we need to actually program it. And we're going to use this chance to practice the balance between decomposition and working towards milestones. So this is the situation you're often presented with in homework. You got a problem to solve and you've got this code. It's got this line here, which starts the program. It's got a main, and the main often when we give it to you just has pass in it. And pass does what you imagine. It means don't do anything. And we would like to replace this pass with some actual code to solve some actual problems. And the problem we want to solve today is to have Carol climb up the mountain and go down. So we get to write our solution here. The key concept in decomposition is to start high level. So as we thought about, really climbing a mountain is 3 steps. The first step is to ascend a mountain. and then you're going to plant the flag, and then you're going to descend the mountain. Now, if you read this main, it's beautiful. We talked earlier about how in Code in Place, we want you to learn how to write stylistic, beautiful programs. Part of stylistic, beautiful programs is looking at a main function and being able to understand what the program is doing. When you read this, it says, okay, it's going to send the mountain, plant the flag, then descend the mountain. If I'm curious how it's going to send the mountain, I can always dive further in. But this nice high level of decomposition is just beautiful. Now, I want to be able to solve this problem, and I've decomposed it. But there's this one other thing you have to balance when you're thinking about decomposition, and that's your ability to choose milestones that you can work towards. So I'm going to solve this problem by doing these 3 steps, but I want to make sure that I get ascend mountain correct before I try and program plant flag and descend mountain. That's going to allow me to test as I go. So let's comment out these 2 lines for now. We'll program them later, and let's see if we can solve the first step in ascending or climbing a mountain. So let's define that ascend mountain. We've already talked about how we want to solve this problem. The way we want to ascend mountain is we want to have a loop. Because we don't know how big the world is or how big the mountain is, it's got to be a while loop. You know, Maron taught us about while and for loops, and while was the one that we would do as long as some condition hold. We talked about what that condition was, but maybe you forgot. So why don't I put some question marks and we can think about what that condition is. So while some condition holds, you want to repeatedly do what process? You could write the code exactly here, but to write beautiful programs, I would suggest that we try and come up with a name for what happens in the process inside the while loop. And I think a great name for that process is step up. So while some condition is true, and we can choose that condition in a moment, we're going to be repeating the process of stepping up. What is stepping up? You know, that's another function that Carol didn't know until we define it. Well, stepping up is a bit of a process, and it's something we have to think a lot about. So let's redraw a picture we had before of Carol in one state of step up and in another. So when Carol's climbing the mountain, it's repeating this process of stepping up. But what is stepping up? And what I really want us to think about are what are the preconditions and the postconditions of stepping up? So precondition, what's the situation in the world before you call step up, and what's the situation after? So when you call step up, we imagine Carol is at some ledge. And after you call step up, we imagine Carol's on the next ledge. There's several choices we can make about what direction Carol is facing afterwards. Let's think about that a little bit. There's one really, really, really good choice, and let's see if we can arrive at what that is. In the meantime, you know, we can think, what is step up? Maybe Carol turns left and then moves, and then turns right, and then moves. Now, we're going to repeat this. Whenever you're writing code that you would like to repeat, a good thing to do is to test it on its own first. So let's just try having ascend mountain do a single step up when we run this code. So now I'm going to hit run. It hits the main program, and it went really quickly because it's at 100 times speed. Let's reset and do that a little bit slower. It runs ascend mountain that steps up, and then it has Carol do a move, or turn left, a move, turn right, and a move. Now, if we think about this function, it's going to be really important that we try and decide what's the precondition and the postcondition contract of step up. So what's the precondition? What's the state of the world in which you're allowed to call step up? You can call step up if Carol is on a step of the mountain, and Carol must be facing east. Recall that facing east is the direction that Carol is facing this direction. We think of this as east and this direction as west. If this is the precondition, what's the postcondition? What happens after you call step up? Well, the postcondition is that Carol is on the next step of the mountain, and again facing east. Did you notice how Carol's facing east in the precondition and facing east in the postcondition? And if you think about it, if we call step up twice, And of course, we'll probably want to put this in a loop. I'm kind of showing you how professionals, though, would test as they go. You call step up once, and it goes and it does one step. And now you call it a second time, and he goes and Carol does one step. In all of these situations, the precondition is that Carol's facing east, and the postcondition is that Carol is again facing east. I was very intentional to make that postcondition, the situation Carol is in after you call step up, be very similar to the situation that is in the precondition. In both those cases, they're facing east. Why is that so important? Well, if you want to repeat step up, it must be the case that the world in which you leave Carol at the end of this function is a world in which you are ready to call the function again. So we call step up, and when we're done, since Carol's facing east, that's a valid condition in which we can call step up again. That means you can call step up repeatedly many times. What if our step up had Carol facing north at the end? So maybe you turn left, move, turn right, move, and then turn left again. This seems kind of valid. You're turning left, move, turning right, move, and turning left. You could call that step up. But now we have a big problem. After you do a step up, you're facing north. And when you call step, the assumption was that you were facing east. The postcondition of step up doesn't leave you in a situation in which you're ready to call step up again. And we can run this and watch it crash. So we do step up, and we leave ourselves in a postcondition we're not ready for, and we call step up again. It doesn't do at all what we expected. This is a really important point. Thinking about preconditions and postconditions is crucial when you have loops. If you want to repeat some process, it is really important that the thing you're repeating always has a postcondition that leaves you in a situation where you're ready for the function again. So the postcondition leaves you in a situation that is a valid starting point for the function itself. That way you can call step up, and then call step up, and then call step up. Every time you call step up, it leaves you facing east, and so you're ready. You know that you'll be facing east, which means that this turn left makes sense, and this move and this turn right makes sense, and this move makes sense. If you weren't facing east, if you were left in a different situation, it wouldn't work very well. So now we've got a wonderful function called step up. Now we can think about the ascend. What is the ascend's precondition? Well, this one's pretty simple condition. So Carol is at the bottom of a mountain facing east. And the postcondition is that Carol is at the top of the mountain facing east. Now to do this, we don't know how many times we're going to have to call steps, so we're going to bring back that while loop. And so while some condition is true, we're going to step up. And we're going to keep stepping up and keep stepping up and keep stepping up. When you start this loop, Carol is facing east. And when you finish this loop, we also know that Carol is also facing east. So the precondition of the loop and the postcondition of the loop match. Isn't that interesting? You can think about preconditions and postconditions of the code inside a loop in the same way that you can think about preconditions and postconditions of a function. Anyway, so we can put this comment here. That's a fine place for it. What is this condition? We talked about it before. So if we reset, if we step up, you end up there. Do we want to continue? Yes. If we step up, you end up there. Do you want to continue? Yes. If we step up, we end up there. Do you want to continue? Yes. If we step up, we end up there. Do you want to continue? No. What's true about all of these squares and not true about this one? And we already talked about it. It's that the front is clear. If you're always facing east, here the front is not clear. 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 But here the front is clear. So we can say while front is blocked, we can step up. So we run this program, and now notice how I test as I go. When I program, I'm thinking high level, big picture, how can I decompose my program? But then I also try and test as I go. I want to see that my parts are working. I had already validated that step up works, and now we can validate that ascend mountain works. Great. At this point, we've hit our first milestone. We've made our problem much easier. Now all we need to do is plant a flag and go down. So let's write this plant flag function. That's kind of fun, plant flag. And all I'm going to do is I'm going to put a beeper. You're like, do you really need to write a function for this? It's like, oh yeah, it just makes it so beautiful to read. You don't necessarily need a one-line function, but boy, does it make the main function elegant. This is simply puts a beeper to represent a flag. Okay, what a great activity for Carol on Earth Day. Okay, so if we run this program, I suppose we probably don't need to test this plant flag too heavily, but I always test. Test. It's one of the best things you can do while programming. Okay, we've decomposed the problem. We've gotten pretty close. We've ascended the mountain, plant the flag. Now we just need to descend the mountain. You know, of course, descend mountain is not something that's native to Carol. We get one of these errors, descend mountain is not defined. Have you created a def block with this name? Oh, why, thank you very much, helpful program editor. I have not done such a thing. I should def descend mountain. Now, descend mountain, the precondition is that Carol is at the top of a mountain. And the postcondition is that Carol is at the bottom of the mountain. And remember the guarantee. The guarantee that we're given is that, you know, when you get to the bottom of the mountain, you're also at the end of the world. And at the end of the world. It sounds like Carol's really gone pretty far. Carol ended up at the end of the world. By that, I mean, you're in the very, very last column of the world, because that's where the bottom of the mountain always ends up. Okay, so, you know, in the spirit of decomposition, what is the thing we're going to keep repeating? You could just try and write all your code here. You could just like write it in primitive commands, but it's just so much easier to write if you think about this next level, which is really, we want to repeatedly step down. I want to repeat it, but since the thing I want to repeat is step down, let's see if we can test a single step down before we try and put it in a loop. That's always a great practice. So instead of writing the code for step down, I'm going to define step down as a nice helper function. We'll think about our preconditions and we'll think about our postcondition. Well, the precondition, you know, if we imagine Carol being at the top of this mountain, what is the precondition? So Carol is on a step of the mountain facing east. And the Carol postcondition should certainly be that Carol is on the next step of the mountain. But which direction should Carol be facing? You guys already know this. Carol should be facing a direction which matches the precondition. We want to be repeating step down. That means the postcondition should be a very similar situation to the precondition that allows you to call step down after step down. So we should definitely be facing east. Okay, so what is step down? Get our handy pen out. So in step down, you know, you've got a situation like this. You have Carol over here and you want to get Carol down over here. That's a good time. We know Carol was facing east. Well, if Carol was facing east, let's move. And if you move, that takes you one step here. And then we should turn right. And then move so we drop down. And then we can turn left. Okay, so, you know, at this point, we've got descend mountain and it's just calling a single step down. Should I keep coding? No, I should pause and test. I'm about to put step down into a loop. We're going to try repeating step down, but it's always good to test it in one situation before you try repeating it. And then you can ask yourself, would it be good to repeat it again? So let's run this program. Make Carol go a little fast. Yeah, climb that mountain, Carol. Ah, Carol got to the top. Carol did one step down, and this looks pretty good. You know, we could just try calling step down twice to see if it's a repeatable thing. So let's run. Carol gets up there, steps down once, and steps down twice. Fantastic. We've got a situation which can be repeated. Step down has a postcondition facing each, which is a match for the precondition. After you call step down, you're in a situation where you can call step down again. Now, of course, you know, if you did move, turn right, move, technically, you've stepped down, but now your postcondition is facing south. And this is the same thing we saw before. And facing south is not a valid match for facing east. You know, the end of this condition is not a match for the beginning. That means if you call it twice, oh, it's going to be trouble. Oh no, what's going to happen to Carol? Wah, wah. Oh, the most tragic thing. Carol walked into a wall. All right, I can run that again. There goes Carol. We call step down. And the second time we call step down, you just got this front is blocked. That's not a very clear message from the IDE. It would be great if Python could tell you, oh, programmer, really you had an intellectual issue, which was that the post condition of step down didn't match the precondition. So you couldn't call it after itself a whole bunch of times. Now, if it could have said that, then you'd be like, oh yeah, I really want to make it sure that the post condition facing east matches the precondition. So we should certainly be turning left afterwards. Yeah, programs don't always tell you how to solve the problem. That's why we gotta have programmers. Okay, so we don't want to call step down twice. We don't want a for loop because we don't know how many times. Mountain could be different sizes. We want to do something while some condition is true, we want to step down. So we repeat that challenge. We think, what is true here, 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 but not true here? Because this is where we want to stop. Okay, what's true here? What's true here? What's true here? What's true here? And what's true here? Well, here your front is clear. 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 It's blocked. So if the front is clear, you should repeat. And the front is blocked, that's how you know you should stop repeating. So we say, well, front is clear, step down. And this is just a beautiful program to read. You know, the main function, it's not the most helpful comment. It probably should say something like, Carol is going to climb this mountain. But you know, when I read the code here, it's so clear to me how the programmer is approaching this problem. They've broken it down into 3 parts: ascend mountain, plant flag, descend mountain. As a reader, as a writer, it's great to understand. If you jump in descend mountain, you know, we're going to repeatedly step down. Oh yeah, that's elegant, easy to see. And the programmer has left this really helpful comment. By the way, these comments can be written in 2 ways. You can use the triple quote, or you could use the hashtag for each line. Both are fine. But this makes it really, really easy to read. So while front is clear, step down, and then what is step down? It's move, turn right, move, turn left. You know, at some point, these functions become one of the 4 commands that Carol knows. But do you see how many layers we put in first? This is the art of programming. And it might seem simple. You know, Mountain Carol, maybe it's something that you could have imagined programming without decomposition. But trust me, if you want to write beautiful big programs, you're going to want to be able to decompose. Okay, let's go celebrate. Have Carol climb that mountain. Go, Carol. Go, Carol. Yeah! Good job, Carol. I wonder if it only works for this world. You know what we really should do? What we really should do is, instead of just testing on mountain 1, Carol, notice how if I look at my files, I've got mountain 1, mountain 2, mountain 3. Let's see if Carol can do mountain 2. Dun, dun, dun. Reset, save, and run. Oh my God, what a big mountain. Will Carol ever be able to climb this mountain? It's so much bigger than anything Carol's ever climbed before. Duh, Carol ascended. Go, Carol. Go, Carol. Go, Carol. We believe in you. It's such a satisfying feeling when you solve a problem. Like, it brings such warmth and joy. Like, there's no world in which I've been given more interesting puzzles than when I'm learning to program. And when you get that puzzle, it's just such a thrill. Okay, so it's worked on mountain 1 and mountain 2. What if we tried mountain 3? You're like, no, what is mountain 3? Actually, mountain 3 is a much smaller world. Sometimes the really small ones are the ones that are hardest. Like, sometimes bugs pop up when you try it on small worlds. Anyways, we have written a generalizable solution, and we wrote it in such an elegant way. This is really easy to understand code. I think there's 2 types of code. Sometimes you write programs that are so complicated, there's nothing that's obviously wrong with them, but if something goes wrong, oh boy, is it hard to figure it out. But the sort of code that I want you to write is the code where it's so clear and it's so obvious that it's obvious there's nothing wrong with it. Like, if there was a bug with this, I could get really, really, really analytical and think about it. But when I read this code, it's just so simple. I've made it as simple as I possibly could. And that, my friends, is beautiful style. That is how you get the art of programming, so you can make big, wonderful, amazing programs. If you can practice this, having really elegant, simple to understand programs, you'll be able to build big, wonderful things. Okay, now, next I want to show you another piece of program to kind of build this idea of style. This program is called Do Your Thing. Well, let's load Do Your Thing. And if we look at Do Your Thing, Carol, let's read this for a second. Your task right now is to tell me, what does this program do? Here's do your thing, Carol. It's got some stuff going on. It's got some function A. It's got some while loops. And you're like, you have no idea, right? It's impossible to tell. And if there was a problem with do your thing, oh my God, if it was your job to fix it, that would be such a nightmare. It turns out do your thing solves Mountain Carol. This code is functionally equivalent to this code. But there's one big difference. It's impossible to understand this. There's no decomposition, there's no comments, there's no concept of preconditions and postconditions. If something about the specification of the problem changed, which of these two would you rather have to edit? Like we said down, mountains always were 2 steps up for every 1 step over. Would you rather edit this code to make it work, or would you rather edit this code? And there's really one good answer, which is like, do your thing, Carol, is not very easy to understand. Good style, good programs will lead to wonderful solutions that you'll be able to build. Anyways, there you have it. Okay, I have a couple pro tips for you guys. We've talked a lot about functions, and we've talked a lot about how important they are. You know you need them, and you know that they should be good functions. They should have some nice style. But maybe at this big point, you're like, I'm just starting, Chris. Like, what's a good function? What's not a good function? I tell you, it's an art form. But I can give you some pro tips to give you an idea of like, is your function a good function or not? So a couple pro tips. A good function should do one conceptual thing. So, we had a nice function. It was ascend mountain. It just does one conceptual thing. Then we had another function. It was called step up. It didn't do more than step up. It just did what it said it was going to do. It just did one thing. It could be a big thing, could be a small thing, as long as it's one thing. Another pro tip is like, if you look at the name of a function, like step up, it should give you a pretty good idea of what the function is going to do. And if it does something different than what that name gives you idea of, is a problem. And if you read the function, it's like, I have no idea what this does, that's also a bad sign. Your function shouldn't be too long. Now, that's a little bit of a, who gets to say is too long or not too long? And the answer is, it depends on the task. While you're programming, especially in Carol, here's a rule of thumb. If you ever have a function that's longer than, say, 10 lines long, or it goes deeper than, say, 3 lines of indentation, it's probably a little bit too far. Another great thing is like, if you have some function and you get to reuse it a whole bunch of times in different contexts, that's a great sign that you've written a really nice and useful function. A great example of something reusable is like turn right or turn around. Turn right, we get to reuse it all the time. It's just like a truly, truly utility function. So if you write a function and you can reuse it, good sign. And then finally, well commented is very useful. When somebody wants to go check out a function, first they read the name, get a sense of what it does. Then they read the comments, and that gives them more details of what happens. And it should be only if they can't figure it out from the name and the comments that they should have to read your code to figure out what the function does. So these are all a bit of the art form of writing stylistic programs. But that's about, the art and science of computer science. Like, that's the difference between just coding and actually writing something that is usable in the real world. You're going to realize that most of your time is spent fixing bugs instead of creating programs. Like, once you create an error, it takes a lot longer to solve it. And to that end, this is like why style and good functions and decomposers, one of the reasons it's so important is because it helps you avoid putting bugs into your program. I like to think that there's 2 kinds of programs. There's one kind of program that's so complicated that there's nothing about it that's obviously wrong. And you'd have to really think and try and figure out if there is in fact anything wrong. That's one kind of problem. Another kind of problem is so simple, like a program, it's so simple, you read it, it's so clear that there's obviously nothing wrong with it. You want your code to be in the second category. You want your code to be so clear that it's really, really obvious that you have not made a mistake. That's where you'd like to be. Okay, now we're going to go into more examples, but I thought I would give you a little intermission to talk about some common problems that people have at this point in programming. One common problem is this idea of an infinite loop. And I thought I'd give you a real world example of infinite loop. There's this joke that why did the programmer die in the shower? It's like, oh, because the instructions on the water bottle or on the shampoo bottle said lather, rinse, repeat. And a programmer would lather, then rinse, and then repeat. And then lather, and then rinse, and then repeat. And there's no stopping condition, so not important. Terrible joke. An infinite loop is a loop that never ends. So you hit a loop and you can never get out of it. So here's an example. Carol's in this situation and is about to hit this loop called while left is clear, turn left. So is the left clear? Yeah, left is clear, turn left. Is left clear? Yeah, left is clear, turn left. Is left clear? Yeah. And this never ends. Carol will never exit this loop. We call this an infinite loop and you want to avoid them. Anytime you enter a loop, think about how you're going to get out of it. Okay, another common error, and this is probably the most common error for people when they're programming, is every time you have a loop, when you finish the loop, you go back to the start of the code. That means that at the beginning of a loop, you kind of assume some things are true about the world. So for Meron's example of jumping hurdles, he makes some assumptions at the beginning of his for loop. At the end of the for loop, the condition, the state of the world has to match the beginning of the for loop. So we say like the context at the end of a loop, the post condition of the loop, we want it to match the assumptions of what you were assuming when you went into that loop. Okay, that's what we got for our little sides. Okay, so at this point, we've talked high level about what decomposition is. We've gone in and actually done some decomposition ourselves with Mountain Carol. And so now it's time to do a little bit of cleanup with our Roomba Carol.